Hello, everyone. Good morning, good afternoon, good evening, depending where you are. My name is Shannon Holmes. I'm a medical physicist here with Standard Imaging, and I'm excited to be able to talk to you today about small field scanning. We've got a question that was typed in already about CAMPEP credits, and no, unfortunately, CAMPEP has decided that presentations from a vendor that relate to the vendor's product. If it's the vendor presenting it, we're no longer allowed to give CAMPEP credits for that. So if you have, if you wouldn't mind reaching out to them and letting them know that you think that this is an appropriate sort of presentation for CAMPEP credits, we would love to be able to offer those again. But as of right now, that's not something that we're able to offer. So without further ado, I guess, I do want to stop and say thank you to all of you for the work that you do. Cancer doesn't put itself on hold in the middle of a pandemic, and we're very happy to be supporting you in the work that you do. It is critical for your patients, and we thank you for all that you do. Just a little bit of housekeeping. I am recording the webinar today. So that if you have to step out in the middle, I know clinical life can be crazy, feel free to look later at the recording, or if there's something you want to come back to, or if you just want to share it with a colleague, you could certainly forward that as well. But we will send out a link to the recording in the next couple of days. If you have questions throughout the presentation, please feel free to enter them in that GoToMeeting dialog box. I'll be happy to answer those as they come up as best I can. If I miss it somewhere in the middle, I will try and circle back to those at the end of the discussion. So a little bit about us before I get going. Standard Imaging is based in Middleton, Wisconsin, which is just outside the capital city of Madison. It was founded in 1989 with just a couple of products, but has grown in those 30-some years to design and manufacture here on site a full suite of QA products for radiation therapy. And although I have this nice summer picture here, it looks a little bit more like that out the windows at work right now, which is beautiful if you're a cross-country skier like me, but I know a few people aren't so excited about the snow. Anyway, back to small fields. Conditions for small fields, I guess, is a good place to start on this. The TRS 483 report, that's a joint small field report from the IAEA and the AAPM, defines small fields as having at least one of these conditions, either loss of lateral charge particle equilibrium on the beam axis, partial occlusion of the primary photon source by the collimating devices on the beam axis again, or that the size of the detector is similar to or large compared to the beam dimensions. So when we're talking specifically about scanning, one of the biggest things that impacts these measurements is the detector themselves. So I want to just go through a few ways that your detectors impact your measurements. So first and foremost is detector size and shape. We know there's volume averaging across the region that's being integrated by the detector. And so it's very important to understand your profile. I know that's what we're trying to measure with the scanning, but to have some understanding of it relative to your detector's spot size. And what I mean by spot size is this full dimension that it's integrating over. So we're including in our definition of spot size, we're including this the wall of the chamber as well as the actively collecting air volume, in this case for the ionization chamber. But this is the active region that's affecting your measurement. We would like to determine the beam penumbra accurately as you're doing your scanning, and that fall off, the integration of that fall off, as well as any peak, like in this gamma knife plot from that I have from a publication from Meltzner and DeWord. Your detector will average over that, and I'm sure all of you know that, but it's a good thing to be aware of. If you're looking at the profiles, knowing that each of those measurements is an integration over the volume of your detector. Positioning obviously is a much more critical item with small fields than it is with the larger fields as well. Where a slight offset in the center of your field or your for say your PDD scan is going to make a big difference in the actual measured value that you get. Whoops, wrong way. Second way that your detector impacts your scanning is by perturbing the beam right there at the point of measurement. So you're changing the way that the radiation is interacting. You're changing the fluence right there at the point that you really want to know what it is in water, because you're replacing water with your detector, whether that's a lower density detector like an ionization chamber, a higher density detector like a diode, or something that's a little bit closer to water, whether that's a liquid ionization chamber, a diamond detector, or a scintillator, something like that. So questions to ask: how big is your air cavity in your ion chamber? Because that will affect how much perturbation there is. What density is your diode? Is your diode compensated? So compensation for a diode is usually a small air gap next to the higher density portion of the diode. And this is intended to kind of balance the radiation interaction with the diode. This can be very good if you're in the energy that compensation was kind of tuned for. It may not be as ideal if you're trying to cross a broader spectrum. There are published corrections. Usually these are related more to the output of your beam than necessarily scanning corrections. But it is important to keep in mind because some of these published corrections can help you understand the behavior of your detector as you move to scanning these small fields, if it's going to under-respond like an ionization chamber or over-respond more like a diode, how to expect that behavior to change. And it does actually affect the tails of the field as well, which I think I have a note on here later on. These are a couple of published corrections on some various detectors with depth for scanning fields, just as a reference from Paolo Franciscan. Third way that your detector is going to affect your scans is signal. So with an ionization chamber, your signal is proportional to your collecting volume. So as you go down into these very small microchambers for scanning, you need to be sure that your signal to noise ratio is sufficient to give you a reasonable reading. Sometimes if you've got a high electronic noise floor or background signal, you may actually measure a little bit too high in the low dose regions because you're basically bumping up against that noise floor. It's a little easier to troubleshoot or to understand your electrometer behavior and the ranges often with our calibratable electrometers than necessarily the ones that are attached to a water tank. And so that's something just to consider. We think about it a lot when we're doing our calibrations. We don't necessarily think about it as much as maybe we should with the scanning tanks, because the small signals that you get from these small ionization chambers do require an appropriately sensitive electrometer. With a diode, you do get a larger signal than from micro-ionization chambers, so the low channel on your electrometer or the low end of that signal range on your electrometer is a little bit less critical. Also make sure, if you're looking at those electrometers, make sure you're looking both at, or primarily, I guess, at the current and not just the charge that you would collect over whatever length of time, although both are critical. Signal to noise ratio, I mentioned already, is important. If you have electrometer leakage, if you haven't properly warmed up your electrometer, you could have issues with the signal to noise ratio. It's also important to make sure that if you can choose an electrometer range for scanning, you choose the appropriate range that matches the signal that you would expect to get from your detector. Be aware also that this needs to, you need to consider both the in-field signal level. So if you're in the high range and the in-field signal level, you may not get as good a results over in the tails if you're bumping down against the low end of that high range. There can be triaxial cable effects. This again matters a little bit more for your point measurements if you're unwinding a really long cable, but there are some triaxial cable effects that can affect your SNR and your minimum measurement current as well. Accuracy of your detector is also critical for scanning, just like it is for output measurements. You need to understand the energy dependence Diodes often have a low response to low energy. And so they can under-respond out of the field and give you an underestimation for the low dose region, especially in your SRS patients as you're scanning these small fields. I mentioned the compensated diodes. Here's where you really need to think about, is this really fitting what I'm wanting or what I'm measuring, or is this not going to, or is it making it more complicated, not going to help me with my measurements? Corrections may be depth dependent, particularly for a detector that has a higher energy dependence. That energy changes as you increase your depth with your scan. So that would affect, again, your PDDs, maybe a little bit more than your profiles, except out at those tails where, again, you get a different spectrum, but something to be considering as well. Angular dependence of your detector is a little bit less critical when you're doing just face-on scanning in a water tank, but it is important to make sure that you're using your detector in the orientation for which it was designed. If you turn your ionization chamber end on, or if you turn your diode on its side, make sure that that's actually been characterized before you expect to be able to use it. So dose rate and dose per pulse dependence also are not quite as critical with the scanning as they are with the, I'm trying to open questions at the same time. Sorry, I shouldn't do two things at once. As they are with output measurements, because you're usually measuring in a consistent fashion. So with relative scanning measurements, usually the dose rate or the dose per pulse is being maintained. Other than I'd add a caveat that as you go to your smaller fields, then that can affect dose rate or dose per pulse. And therefore, if you have a detector that is more highly sensitive to those changes, or you're at borderline saturation or something like that, then that can affect your scanning measurements as well. So what's the best option for us? We've got three main ones, right? So they're ionization chambers, and I'm listing the A26 here, which is our micro-ionization chamber. The A28 is our standard scanning chamber. There are diodes, like the Exradin D1V scanning diode, and then a water equivalent detector, the Exradin W2 Scintillator. So all detectors, whether they're from us or from somewhere else, all detectors have both strengths and limitations. So your best solution, especially if you're doing a broader range of fields and not just the very small fields, your best solution is still a good combination of detectors. You're not going to find one ring to rule them all, one detector to rule them all, that's going to do everything from your 2 millimeter or your 4 or 5 millimeter field all the way up to 40 centimeters. There was a question, let's see. Thank you for the comment about CAMPEP. I do appreciate that. So how is triboelectric effect relevant? Can I please expand on that a little bit? Yes, I'm sorry. The triboelectric effect is something that if you have a tightly coiled cable and you unwind it, then there is a relaxation that happens within the cable that can create a current, a very small current, but if you're measuring very small amounts, then that can affect your measurement. This was back up at a prior slide. If you are looking at a, say, 30-meter cable, that's been unwound, so you can have your electrometer for your TG51 measurements outside the room. You may have a long time, a few hours actually, in which that cable is relaxing and still generating these spurious charges. So if you never hold a zero, if you zero and re-zero and re-zero and it never seems to stay zeroed, that might be something to investigate. With just plain scanning measurements where you just got the chamber cable attached to your water tank, there are usually fewer issues with those big triboelectric or with triboelectric effects. But it is something that I like to point out. It was something I didn't know until fairly recently when one of our engineers pointed that out to me. So The A28 is our scanning chamber. Somebody asked that. The semi-flex is not a standard imaging. The Exradin A28 is the standard imaging scanning chamber. So the A26 is the microchamber that I would recommend for these small fields. This was designed very deliberately to try and ensure that this is a reference class chamber, and it was designed as a result of some investigations through the University of Wisconsin-Madison into the behavior and especially misbehavior of microionization chambers. And so some of the things that we considered when we were manufacturing this one or designing this one, within those constraints, of course, of a well-behaved reference class chamber, was that chamber spot size. We wanted to make this a spherical chamber or spherical active volume in order to ensure that you're integrating over the same volume, the same space, no matter which orientation your chamber is in. We modeled the electric fields to verify that shape, and then we tried to make this as small as we possibly could. So the scanning chamber, the A28, is a 0.125 cubic centimeter chamber, like the rest of the standard scanning chambers. The A26 is down at 0.015. But to tell the volume doesn't tell the whole story. So the A16 is our smallest chamber. This one's been on the market for quite a few years now, and it's the 0.007 chamber. Its spot size is 3.5 millimeters. So that's this sphere, this circle that encompasses all of the active region. The A26 is less than a millimeter larger, and you get twice the volume. So here, actually, this is a bit of an advantage, because of the behavior of the chamber, because of the way it was designed. You don't have those polarity effects like you do with the A16, but you've doubled the signal that you're getting with less than a millimeter increase in spot size. So that helps quite a bit with SNR, especially for water tanks where those electrometers were not necessarily designed for these teeny tiny ionization chamber signals. Strengths of the ionization chambers. The A26 is a reference class chamber, so you can trust that it's going to be a long-lasting, stable chamber. It does have that spot size that's independent of orientation. It is spherical collection. And ionization chambers are familiar technology for most physicists. We're used to using ionization chambers for most of the measurements that we do, and therefore we're comfortable with them. We're comfortable recognizing when they're not behaving properly, and we're very comfortable using those. Limitations is you can only make an ionization chamber so small. You can't make these infinitesimally small, or your electric fields just don't function properly to get the collection or the signal level that you want to have. You do perturb the beam just slightly due to that air volume. So those are some of the limitations of the ionization chambers. For diodes, our scanning diode is the Exradin D1V, V for vertical. There's also a D1H, which is the horizontal version that was made for phantoms. It's exactly the same diode, just a different housing. So these are unshielded diodes. They do have a 1 millimeter diameter spot size. And there are correction factors for your point measurements that are published. There were a couple publications in 2014 looking at both measured and calculated factors. So there's this one from Papakonstantopoulos, and then I had a plot earlier from Paula Franciscan's paper. Strengths of the diodes is, again, they're well-established technology. There's fairly minimal volume averaging because of that 1 millimeter spot size, so you can get a pretty good measure of your penumbra. There's low angular dependence, but again, that's a little more critical for those phantom measurements than necessarily an end-on measurement or scanning in a water tank. Limitations are that they're diodes. They're not exactly water equivalent. And you can see in this plot, it's one of the better of the diodes. It's closer to one, but it's not going to be perfect as your energies are changing there. So the newer technology that I'd love to talk to you about, if you haven't heard of them, are the Exradin scintillators. So the W2 scintillator is the one that's designed for scanning. It's an organic scintillating material. We have fibers with a 1 by 1 millimeter tip and a 1 by 3 millimeter tip. And the reason for that actually is the 1x1 gets you that resolution, especially that orientation independent sort of resolution. The 1x3 matches our original scintillator, which was the W1. And also gives you a little bit higher signal level for those fields where that volume averaging is acceptable, so that you have a little bit less concern about your signal to noise ratio. The beautiful thing about the scintillator is that it's water equivalent, completely water equivalent, for these megavoltage photons and electrons. And so you don't have to worry about the changes in energy or response with energy. You don't have to worry about the perturbation of the beam right there at the point of measurement. You are actually measuring the dose to water right where you want to. The bad part about the scintillator is that it does require a correction for the Cherenkov effect. So this is the spurious light that is produced actually within the optical transfer fiber. It's a PMMA optical transfer fiber, and it's an extra signal. It's not really noise, it's more of a stem effect. And so we have a method then for removing that from the measurement via Cherenkov light ratio. That's what this CLR stands for. But it's not an absolute dosimeter like an ionization chamber is that can be calibrated. It is a relative dosimeter, so it does need periodic recalibration, characterization type measurements, because the plastic does degrade as the material accumulates dose, and so your signal level will decrease slightly. We use a 2-channel chromatic correction to get rid of that Cherenkov. So here it shows just a kind of rough plot of what our blue scintillator scintillation curve looks like. Cherenkov is a broad spectrum light, and so what we're really measuring is the combination of those. But we split the spectrum into 2 portions, a blue portion of the spectrum and a green portion of the spectrum. And we have you do 2 characterization measurements. This is an image or a picture actually of the bracket that we have for the water tank for doing those Cherenkov measurements. You would do a minimum fiber configuration with the fiber coming straight out of the field, and then a maximum fiber configuration measurement with the fiber wrapped around and coming across here. And the idea here is that you're keeping the dose to the scintillator the same and changing only the Cherenkov contribution. Sorry, I should have put the equations up a little sooner. But we calculate this correction factor called the Cherenkov light ratio by taking the change in the blue signal divided by the change in the green channel signal. And this gives us a correction factor we can multiply by the green signal for any subsequent measurements to give us the removal, or to allow us to remove the Cherenkov from the blue signal. You can give it a dose calibration. This isn't necessary for scanning measurements that are all relative, but you can tie the output to a known dose if you give it a dose with a reference field size. These little tabs here on the bracket are intended to mark, actually not intended, they do mark the active point of measurement of the W2 1x1 fiber. So you could center your field there for your dose calibration measurements. For scanning, we actually have an acrylic sleeve that goes over this fiber in order to be able to extend it out from your standard chamber holder. But it will fit with any water tanks, not just the standard imaging water tank. There we go. PowerPoint's mostly behaving today. So with the W2, we were able to improve the optical sensitivity from our original device, which was just a single point measurement device. That allowed us to offer both that 1x1 millimeter fiber and the 1x3 for the W2. It has its own dedicated optics and electronics unit called the MaxSD for scintillation detector. You can perform your point measurements directly with this device. You can do your Cherenkov characterization with it and your dose calibration with it. If you wish to use your W2 in the water tank, the MaxSD can convert that Cherenkov corrected measurement into a single analog output value. It is also scaled up just slightly so that it's more in the range of the expected signal with your water tank electrometer. So you're not trying to measure these extremely small signals with the water tank or with the triax cable, a longer triax cable potentially for the connection between the Max SD and the water tank. Actually, it's not longer. We send you a cable for that. But it performs that Cherenkov correction for every 10 millisecond integration and then outputs that as that analog output to your water tank. So this just sits as an intermediary, and any signal that comes in, whatever your CLR calibration file that you've saved and selected, will be applied, and that signal goes then straight to your water tank. So strengths of the W2, whoops, I think there was a question. Looks like the W2 can be used comfortably to measure a 1 by 1 centimeter field. Yes, indeed. I know it's gone down to, actually I have proof in the pudding. I think in the next slide, I have, I think, seen 5 millimeter fields measured with it. I'm not sure about the 4, but yes, I mean, the major limitation really is signal level potentially if you've got a low signal strength due to that very high collimation, and the 1 millimeter detector size that gives you some volume averaging there. So strengths anyway, the KQ is 1. If you look in that TRS 483 publication, you'll see values for the W1. The W2 is exactly the same scintillation material, so it is behaving exactly the same way in terms of that beam quality correction factor. So water equivalent for those MV photons and electrons. We've not observed dose rate or energy dependence with it. It has a very small temperature dependence, about 0.1% per degree Celsius. But if all your measurements are at room temperature, then you can ignore any sort of temperature correction as well. It has a very small spot size, which is quite useful for scanning these small fields. And the fiber is MR compatible. As long as you keep the Max SD outside the 5 Gauss line for your MR Linac, you can actually use it with MR Linacs as well. So limitations are that it does require occasional recalibration. It's not a reference, or excuse me, a calibratable detector in terms of sending it in for calibration. But again, for scanning, that's not such a critical issue. That's more critical for your output measurements. Another of the limitations is that we've discovered optical signal measurements are not really intuitive to most physicists yet. We're used to ionization chambers and we're used to diodes, and so troubleshooting what's wrong with a scintillator has been a little bit trickier for them. But once you get used to it, it's quite easy to use. The other limitation of the W2 is that because of the low signal and the low SNR, that means that you have to scan more slowly. So we usually recommend you do a 1 second measurement at each dwell point for your scan. This is a small field scan. It's totally worth waiting the time to get that good data and not have to smooth it and correct it and do other processing with it. You know that what you're measuring is really what you want to have, but it's not going to be the one you want to scan your 30 by 30 and your 40 by 40 field with, because it'll be a little bit prohibitive on time. So there was a question about scanning a 1 by 1 field. This is a plot from a publication from Paulina Galavis showing the comparison of the W2 measurements in the red dots with a radiochromic film scan for a 1 centimeter field. Excellent agreement there, even out here with these low signal tails. And we've had a lot of people very happy with it for their scanning since that publication a couple of years ago too. So with that, we're here to help you. We can conquer this small field scanning challenge. I really appreciate your time and your attention today. We're happy to answer questions either now if you want to type them into the question box in GoToMeeting, GoToWebinar, or if you want to follow up with us, either information from the website, contact your sales rep, sales@standardimaging.com. We're happy to help you out with any other questions or information that you would like. So on to questions. Let's see. Oh, what cable equipment or configuration do you recommend as a follow-up to that triboelectric cable effect? Generally, through the conduit is better. The more you can just leave your cable unrolled, the less you'll have to fight some of those issues or setup issues, or roll it. I mean, if you know you're going to be measuring on Saturday, roll it out Friday before you go home, and just let it sit. For small fields, would you recommend getting the CLR for each field size? No, you do not need to do that. Your CLR is the whole point of the CLR is that once you make that characterization, you can apply that to subsequent measurements and not have to continually manually correct for the stem effect. So you would do your CLR in a slightly larger field with that blue bracket for the water tank. You could do it in a 10 by 10. We also have a slab that was used with the W1 that can be used with the W2 that you would do that CLR characterization in a 30 by 30 field. Or we've had users use essentially a slit field, something like a 1 by 15 or a 2 by 20, that they rotate the collimator in order to go between the minimum and the maximum field size. The key points for those CLR characterization measurements are that you need to make sure that the dose to the scintillation portion, the active portion of the detector, is not changing. And there needs to be a significant enough change between the minimum and maximum fiber for accurate characterization of that Cherenkov signal. So if you're going to be measuring up to a 10 by 10 field or a 15 by 15 field, you don't want to do your CLR characterization with a field that's smaller than that. You definitely want to encompass at least the maximum amount of fiber that you'll have in the field for those measurements. I think, let's see, can you please talk to relative output factor measurements with the W2 again? Relative output factor measurements with the W2, you would not need to do a dose calibration, but you would still need to do a CLR calibration or characterization. So you would need to do that minimum and maximum fiber measurement, but you wouldn't necessarily have to give it a dose calibration, give it a known dose and tie your output to a known centigrade or known gray. Below what energy would you start getting energy dependence? As long as you're in the megavoltage range, you'll be fine. Lower energies, we've had a little bit of investigation with some kilovoltage energies, and there are a couple of mechanisms there. One is the water equivalency of the PMMA or of the scintillator, and I don't remember the threshold below which that starts to show up. But any of your megavoltage beams, you're just fine. Let's see. How long can you use a CLR measurement before you need to take a new one? The degradation of the fiber in terms of signal output is about 2% per kilogray of dose to the fiber. And that's really just due to the slight yellowing of the plastic, that it gets a little bit colored, a little bit cloudy under irradiation. It's the discoloration of that fiber that affects your Cherenkov light ratio because it affects the balance of the spectrum that gets transmitted through the fiber. And so I recommend that you check your CLR measurements at least every kilogray or so of dose that you're giving to your fiber, but it shouldn't change. It shouldn't change drastically over that time. So I think that's the last question I have currently listed. Thank you again so much for your attention, everyone. I'll hang out for another minute or two just in case there are other questions, and otherwise we look forward to hearing from you or talking to you in the future.